Welcome. In this lecture, we will discuss about the Tandy's metallurgy and design. So, the concept that I want to cover in this lecture is the role of Tandy's and Tandy's essentials, Tandy's flow diagnostics, and the role of flow control device in the Tandy's, because today Tandy's is not only a receptor for the liquid metal, but it also has some other function like inclusion removal and then providing the liquid at a constant superheat, all these things. So, Tandy's has now today new role because it is the last resort to remove the inclusions. So, that is why there is a lot of flow control device in the Tandy's to control the flow such that we can effectively remove the inclusions. Okay. So, the role of Tandy's, as I said, the Tandy's location first you see where is the Tandy's is located. Tandy's is located basically between the timming ladle and the continuous casting, that is then the continuous casting mold. That is, this is in between these two the Tandy's take place. Why the Tandy's is required? Because it is required to provide the liquid steel at a constant flow rate into the mold. Because if you change the flow rate, then continuous casting is fixed with a constant heat extraction into the mold. So, if you change the flow rate, then it will not be able to cast it properly. Okay. So, flow rate should be constant, and that is why if you use the intermediate reactor, you can maintain the height of the liquid in the Tandy's more or less constant. But if you directly want to feed the continuous casting mold by a Tandy's, then obviously the height level in the Tandy's will change. As a result, flow rate at the nozzle exit will differ. Okay, that was the main idea. That is why the Tandy's is used. Besides, Tandy's can feed a number of caster at a time. That is also another advantage of Tandy's. But today, Tandy's function of Tandy's is not limited to supply the liquid still to a multiple strand at a constant flow rate, but also to remove the inclusions as much as possible, because it is the last resort, as I said, to remove the inclusion from the steel. Okay. This is, if you see, this is the timming ladle and this is the Tandy's, and whatever you can find here, it is the liquid steel stream. This is the stream, and surrounding it you can find one cover is there, and in that cover you purge the argon gas such that liquid steel is streamed or it is poured under an inert argon atmosphere, and this is called argon shrouding of liquid stream. Okay. So, you are shrouding by the argon gas. So, you can find the argon gas goes from the top, also there is some injection in the bottom also, such that you can maintain a completely inert atmosphere through which the liquid stream comes out. Because in this case, because if you have an open stream, then there is a chance from air oxidation, nitrogen absorption and all these things. So, it is essential because that will give rise to a lot of inclusions, and during casting a lot of precipitation will come. So, we do not want that. That is why this is because after timming steel, then inclusion removal station only in the that is the Tandy's, and after that directly goes into the mold. So, we have to be very cautious such that the liquid stream do not expose to the inert atmosphere. Okay. So, and then this is the Tandy's. From Tandy's, because you can control the flow rate to some extent by using the what is called the Tandy's stopper rod. Okay, I will come to that. Now, that is the Tandy's location we have talked about, and then the function is to maintain a constant liquid flow to the mold, that you know. And you, for controlling the flow rate also, besides the liquid height, because there may be slight change in the liquid height, especially during the changeover of the timming ladle. So, you can control the liquid steel also by refractory valves, slide gate or the stopper rod like this. This is called the stopper rod. You can stop it when you do not want, or you can open the nozzle exit as you want, okay, to control the flow rate if there is some problem with the flow rate control. As such, during the timming, when you put the liquid steel from the timming ladle to the Tandy's, you basically maintain a constant height into the Tandy's, because the flow rate at which the liquid steel is emptying to the mold at same flow rate you can pour it. If there is a mismatch, then you can control by the stopper rod. Then the sensors are there to measure the temperature, that is the liquid at which the liquid is coming out, temperature, bath height, that is the bath height, very important, that is the Tandy's bath height, composition, and automated metering devices for input and output flow rates. So you can, what is the input flow rate and what is the output flow rate, you can automatically measure, and accordingly you can control. So this control, sometimes if control is required, you can use this valve, slide gate or the stopper rod for the further control, because you have to maintain a constant flow rate. So this is there. Then as I said, it acts as there is a turn disc no longer just act as a receptor and supplying the metal at a constant flow rate, but also today it acts as an active reactor for removing the impurities, because it is the last resort to remove the inclusions and delivering steel with the uniform superheat. That is also very important. That is why temperature is also measured. But if you want to supply the liquid steel at a constant temperature at the exit, you have to maintain the proper flow rate inside the bath. That will come to that thing. So these are the additional function today. Turn disc essentials, that is the liquid steel pouring without atmospheric interaction, just I said. There is the from Teeming ladle with an inert gas shrouding, and then this is the inert gas shrouding I have showed you already in a better way. This is the shroud that I showed you in the previous one. The shroud looks like this is the bell shroud, and the argon gas is pushed into it and liquid steam comes through inside the shroud. Okay. Turn disc lining. Turn disc lining, you can find there is a monolith lining. A permanent lining using bauxite and zirconia is there, that is just after the steel shell. In the turn disc you have a layer that is called the permanent lining, that is made of bauxite or the zirconia, and then you have a wear lining over it. You can find a monolith wear lining, not by brick, but it is ramped material. Okay, it's monolith and it is made of basically spray of 60 to 90% MgO, which is just sprayed. Okay. So, and that the spray contains around 60 to 90% MgO. So, it is very MgO rich monolith layer you can produce by spraying. And flow control device, pouring boss, you can find that here is a pouring boss. When you are steaming the liquid steel, when you are tapping that is you can steaming the liquid steel from ladle to the turn disc, you can find where the liquid will fall directly. It will have a huge impact on the refractory valve. So, and also not only that, it will create a lot of turbulence in this region. So, to dam that turbulence and also to avoid the direct contact of the liquid stream to that of the refractory lining, basically you use a pouring box like this. Okay, and or pouring box or pad at the point of contact. And then thermal slag, you have a top slag you have. For basically thermal and atmospheric interaction. To restrict the atmospheric interaction, you use some kind of top slag or the flux in the turn disc top, you use it such that it does not have much of atmospheric interaction. Okay, such that oxygen, nitrogen cannot come into the liquid steel. It acts as a barrier, as well as it also restricts the heat. Okay, because you have to use some kind of flux that is insulating also. Then absorption of NMI, this top slag also act as an absorption for the non-metallic inclusions. That is the inclusion when they float to the top of the turn disc, they should be absorbed by the slag. Okay. So, the slag property should be sufficient such that it can immediately absorb whatever the inclusion coming at the top. And this is basically the calcium aluminate slag with the optimum viscosity is used, because the viscosity also you have to maintain, because if it is too viscous or too fluid, it is not good basically. So, you have to have an optimum viscosity, and that can, and also it will have some other properties like favorable surface tension with the inclusion such that it can engulf the inclusion into it. And it should not contain any carryover slag, because you understand carryover slag contain a lot of reducible oxide like FeO, SiO2, P2O5, all are reducible basically in presence of alumina, and that is this thing. Okay. So, in this, because it is a highly reducing, because the oxygen percentage in the liquid still now is very less. So, it is highly reducing condition, and all these oxides will be have a propensity for breaking, because SiO2 and also alumina, these all the lining are made of the aluminum, okay, most of the cases. So, this SiO2, P2O5, APO will be very reducible in presence of aluminum. So, as a result, they can supply the oxygen into the liquid still, and that can in future form a lot of inclusions. So, no carryover slag at this point is allowed. So, whatever, if you have some carryover slag, you must remove you must remove it before it is putting into the timming ladle. Okay. After the secondary processing, all the slag should be discarded, and that will also contain some amount of carryover slag, such that no carryover slag is retained when it comes to the timming ladle to the TANDIS. Okay. That is very important. Then ceramic filter, you can use the ceramic filter at the TANDIS exit, and it also basically arrest the inclusion to some extent. Like the filters are usually zirconia alumina filters are used, and it can also inclusion, but inclusion is much smaller compared to the porosity into these filters. So, it is not in the just like what you know the filtering method, there is the inclusion will not be allowed to pass through these pores. They can easily pass through the pores, but how they are get arrested into the filter, it is by because this inclusion get attached to the surface of the pores. Okay. So, that is the way. Inclusion is much smaller than in the filter, pores in the filter. Inclusion get attached to the pore wall and get sintered at high temperature. So, that is the way this ceramic filter basically arrests some amount of inclusion, okay, into it. So, TANDIS designed with dam and weights to develop favorable flow characteristic for enhanced TANDIS performance. Okay, that is the thing, because I will just talk about what type of flow characteristic we are talking about. And another thing is that you can see the aim is to direct the liquid still through the top slag, and for giving inclusions the last chance to annihilate into the slag, that is I said. So, the liquid flows, it should move through the top slag and then come to the exit. Okay. So, that type of flow pattern, and that is only possible by some kind of plug flow type of flow. So, I will talk about that. Plug flow is one of the real flow. There is idealistic flow, that is called the plug flow. I will come to that reaction later on. Anyway, so aim is that thing, that is the TANDIS design. So, that is, as I said, to promote the plug flow. Plug flow can give this type of flow, such that the liquid will move at constant, all the fluid element will move. In a plug flow, basically all fluid element move in a particular velocity, okay, and they have a constant residence time, and they will follow a particular path. So, you can make a plug flow in such a way such the liquid still move through the inclusion top and then comes to the existence. So, during their movement to the in contact with the slag, basically the inclusion will get removed. I will come to that. Then eliminate the short circuiting of liquid and the dead zones. If some liquid directly, that is after pouring from the timming ladle, if directly come to the exit stream directly, then it is called short circuiting, because some of the liquid can be some of the fluid element can be arrested into the reactor in the form of CSTR, continuously stirred reactor. Basically, a reactor is a combination of plug flow reactor and continuous stirred reactor and the dead zone also. So, that will come to that thing, but eliminate the short circuiting of the liquid at the dead zone, that is very important. If liquid directly comes from that thing to the exit, from the timming ladle to the exit, that is after pouring, and then it directly come to the exit, that is called the short circuiting. In that case, liquid will leave with a very high superheat. Okay. So, that we have to stop it, and also this liquid will don't get any chance for the inclusion removal. Maintaining a constant superheat from the exit stream, that is thing, if I want to maintain a constant superheat, as I said, you should avoid this type of short circuiting. And also reduce the mixture, that is also very important, because if you have a because the reactor, any real reactor is a combination of ideal reactor like plug flow reactor. In plug flow reactor, the fluid moves at a constant velocity, fluid element in a continuous, and so all the fluid element in a plug flow reactor has a constant residence time. In case of a continuous reactor, there is a complete back mixing into the liquid, and the residence time of the liquid in a continuous stirred reactor is there is a wide range of residence time. Some particle, some fluid element can stay for a longer time, some fluid element can stay for a very small time. So, from a continuous stirred reactor, liquid can come out immediately or liquid can come out after a long time. As a result, whatever that liquid can come out with a high superheat as well as it can come out with a very low superheat, because those will reside for a longer time, they will lose the heat while staying into the reactor, and when it is coming out they will report at a very low temperature. So, that problem is there in the CSTR, and that is also an ideal reactor. So, in a real reactor there is a combination of plug flow reactor, then CSTR, as well as you have a dead zone. Okay. So, this mixed reactor is not a good from constant superheat point of view, because some fluid element can stay for a longer time, and when they come to the exit stream they will give a very low superheat liquid. And also reduce a erosion of the refractory and atmospheric interaction. So, you should design there is a fluid flow in such a way such that the fluid flow do not have much interaction with the refractory wall, that is the shear stress at the wall should be as low as possible, such that you do not have much erosion, and also in atmospheric interaction you can avoid by using the slag. And also damp, that is the damp near wall shear stress, as I said, and top flux to protect from atmospheric interaction, as I said, that is also really required. So, these are the aims. So, these were the aims. Now, I come to the Tandy's diagnostics. So, real reactors can be analyzed in terms of ideal reactors, as I said. So, ideal reactors, this is the plug flow reactor, as I said. You can find the all fluid element are moving with a constant velocity. So, it is entering and coming out. So, all the fluid element has a constant residence time. This is an example of a CSTR. These are basically stirred, and it is stirred in such a way, suppose if you give some amount of pressure at the inlet, immediately the concentration everywhere will be the average concentration. So, concentration gradient will not be there, it is continuously stirred, it is continuously mixed reactor also, it is said mixed reactor. So, ideally mixed reactor. So, if you give some pressure, immediately it will be distributed everywhere, and concentration everywhere is the average concentration. There is no concentration gradient inside. Another thing is that all this fluid element, it will not come out. Some of the fluid element come immediately, some of the fluid element come after a long time, and there is a distribution of residence time. So, the fluid element come with the distribution. As a result, the liquid, if you consider the temperature of the liquid, it will vary with time, because heat is losing from the walls. Okay. So, if the liquid stays for a longer time, it will report to the exit stream in a lower superheat. Real reactor is a combination of these things. Suppose you have a plug flow reactor, this is the CSTR. So, it is a combination, and some dead zone is also there here. What is called dead zone? Where the velocity is very less, say 5 order of less than the average velocity, or that is called the dead zone. There basically their liquids are not moving. Okay. So, in the Tandy's diagnostics, what is the aim basically? People do is estimate the relative volumes of the plug flow, CSTR and the dead zone from actual C curve. Basically, you have some curve that is called the C curve, you can analyze the C curve. C curve is basically, if you analyze the exit concentration, you can add some amount of pressure, and at the exit you can measure the pressure concentration with time. Okay, then the dimensionless concentration, if you plot against the dimensionless time, the curve that gives it is called the C curve. And by analyzing the C curve, you can tell what type of reactor it is, what is the proportion of different flow regimes. I will just give an example. So, suppose this is a C curve, okay, and this is an actual thing, this is also another actual and real ideal reactor. C curve for what is that called? C curve for your plug flow reactor looks like this, because initially no concentration at the exit, and suddenly you get a spike, that is all the concentration come, and after that there is, because the fluid is moving with the same velocity from the input end. So, if we add some tracer, the tracer immediately will not come to the exit stream. So, when all this tracer element will move with the particular velocity, and then when all this fluid element containing the tracer will come to the exit stream, they will show the peak, sudden peak. And after that all the tracer will go out, and then whatever the fluid will come, there will be no tracer, because in the plug flow reactor there is no back mixing also. So, this is the typical C curve for a for a plug flow reactor, and a typical C curve for a continuous star reactor is looking like this exponential curve. There is a dotted line you can find. This is also for the CSTR. It is an exponential curve. So, there is a distribution of residence time of the fluid element, and all these other curves, these curves are for the actual some curve, and then okay. So, and this number you can find, it is called the dispersion number, d by UL, where d is the effective diffusivity, u is the velocity, that is the circulation velocity in the reactor, L is the characteristic length, and d by UL is a dimensionless number, and it is called axial dispersion number. So, since there is no mixing in case of the plug flow reactor, the axial dispersion number is 0, because diffusivity is 0. And in case of CSTR, you can find this axial dispersion number, this number is infinity, because there is an infinity back mixing, the total back mixing. And these are all actual reactor. You can find this dispersion number is 0.1, it looks like this, the curve looks like this, and it contains obviously a combination of plug flow reactor and CSTR. And this curve, if you see, it curves, obviously it says there is a significant amount of the plug flow reactor. This is the signal of a plug flow reactor, okay. So, and after that it also contains the CSTR also, some portion. So, we will now calculate what is the amount of the plug flow and all these things. So, that is the theta p. You can find there is the first concentration appear at a time of dimensionless time of 0.25, right. At 0.25 you can get a spike, before that there was no concentration. So, that means a certain portion is a plug flow reactor, and so that theta b is 0.25. I can see from the curve, there is this curve, I am just analyzing this curve. So, at 0.25 we can find that is the theta p LCM, that is the plug flow reactor, dimensionless time. So, this you can define as Tp by that is the T bar. T bar is basically nominal residence time. How do I define the nominal residence time? Total volume divided by the volumetric flow rate, because in any continuous, these are all continuous reactor. So, continuously you are feeding from this end the fluid, and this end the fluid is coming out at the same rate, that is Q is the fluid volume flow rate, is input and the output also. So, Q is the volume flow rate into the reactor, and V is the volume, then V by Q is the nominal residence time. And Tp, how do you define? Tp is the plug flow residence time. How do you define? That is the volume of the plug flow divided by the volumetric flow rate. So, then if you define it, then it becomes theta p becomes Vp by V, that is equal to 0.25. I get one equation that correlates the plug flow volume to the total volume. Now, I need to get some other equation. Now, theta mean, how do you define the theta mean? There is the mean residence time. Mean residence time is T mean by T bar. Again, T bar is the nominal residence time, and T mean, how it is different from nominal residence time? That means I am just subtracting the dead volume, because dead volume will not participate into any tracer concentration, because it is considered stagnant, and if some tracer is there, tracer will not go there, and if it is there, then it will never come out, okay. So, thing is that we are just extracting, that is removing that portion from the total volume. So, V minus Vd is the actual volume participating in a mass transfer, heat transfer, anything. So, V minus Vd and divided by the Q, and this is basically the T mean, and this is the nominal residence time. So, basically theta mean you can divide V minus Vd by V, and again theta mean you can define in this way, because you have exit concentration, you know Ct. Ct is the concentration of the tracer at any time t at the exit stream, okay. So, Ct T into dt divided by Ct into dt. Ct into dt basically is the your total concentration that is coming out, and Ct into T. So, if you define this thing, that is the T2 integral, obviously if you take a ratio of this thing, you can get the theta mean. and you can simply get, because Ct you have, that is the, as a function of time you have the Ct in the exit stream. So you can integrate it, divide by this, you will get that 0.6, because all the exit stream you know. So you can calculate this theta mean. So we can put the theta mean. Now we have two equation. This equation correlate V and Vd. This equation correlates Vt and V. So from that I can calculate the Vp and Vd, and then obviously I can calculate the your Vm. Mixed volume is 1 minus 0.25.4. So this way I can analyze. I am just telling you, this is not a I have not gone it through the very rigorously, so it will not be a part of the course, but for your understanding I think it was required how people do that thing. So this way you can identify what is the proportion of plug flow and the mixed reactor and the dead volume are there in an actual real reactor. So this is called the flow diagnostics. Okay. So I can measure the flow diagnostics by simply a tracer experiment and measuring the exit concentration with the time. Okay. Now this is very important, predicted flow path line in the TANDIS without dams at steady state. Okay, these are the without any dams, and we are in a standard. You have a TANDIS and your liquid is coming, liquid stream is heating at this point, and then you can find, and there is no, what is that called, you don't have any pad there. So there is no turbulence arrestor here. So huge turbulence is created. You can find two mixed zone is created around this liquid stream. Okay, in the TANDIS you can find these and these two mixed zone, and you can find the liquid also coming, a part of the liquid is joining this way, that is called the short circuiting. The liquid is getting short circuiting. There is a liquid after poured into the TANDIS, it directly moves to the exit stream, that is called short circuiting. So this is short circuiting. This is another CSTR, and this line basically you can find these are all streamlines. There is the gray lines, these are all streamlines. Streamlines means where the liquid fluid elements are going. So you can see that is, so it is going in the top surface also, but there is a huge dead zones are there. This is white region you can find where there is no streamline. Approximately these are the dead zones. Basically the liquid are not reaching in this liquid for the location. So these are the dead zone. This is the stop order. So you can find. So what you can find here in this case, that is the following undesirable things are visible. One is the short circuiting. So this is the short circuiting. And the presence of 3 CSTR, these big 3 CSTRs are there, and CSTRs are not desirable into TANDIS at least. It is good from the mixing point of view, but in TANDIS it is not desirable, because as I said, the liquid stays into the CSTR or in the mixed reactor for a wide distribution of residence time. So when they will report to the exit stream at different time, and the temperature of the exit stream will be different, so that is not desirable. And then large dead zone, you can find dead zones also large. So I don't, that is, dead zone means you are basically extracting that much of volume from the reactor, and so that much of volume is not participating. So you are wasting some space into the reactor. So now improved design of TANDIS with effect of slotted baffle and dam. You can find I am now putted one dam here. Okay, dam with slots are there, dams with holes here basically. Some nozzles are there, dams with holes, and this is a slotted dam here, but his height is much less compared to this. Okay, and obviously here some pad is there to control the flow. So now this you can find. Now you can see the flow paths. Okay, page off. Yeah, that is the. Now you can see the flow paths, how the flow paths has been changed after you use these dams. Okay, this is the dam is there, two dams are there. One is the dam with holes and taller, and there is the shallow dam with slotted holes. Okay, so what you can find here is that the liquids are moving much more in a plug flow manner. You can see liquid is moving with a constant velocity and then coming out. And when the liquid is there in the liquid still, when it is coming this way, then they will be inclusion will be that is the will have a chance to go into the slag, and also all are moving with the plug flow at a constant velocity and coming to the exit stream. So all the liquid fluid element will report to almost constant superheat. There is no short circuiting. So liquid is coming and then you can move up and then it is coming. So short circuiting has been deleted. So the change in the liquid temperature at the exit stream is supposed to be less. So following desirable things are visible. One thing is the no short circuiting. Second thing is a well designed plug flow to direct the flow towards the top slack to facilitate inclusion removal, and reduction in CSTR and dead zone that will reduce the chance of delivering liquid to the existing at different superheat. Okay. Restrict. So basically, yeah. So if the liquid moves this way, that is, then obviously that is the reduction in CSTR. If you have less amount of CSTR, the liquid still will report at a particular superheat at the exit stream. And if dead zone is not there, then basically you are saving some space into the turn disk and you can increase the productivity. So what we discussed in this case, that is the turn disk is placed basically between a tipping ladle and the concussed mold, okay, and is designed to distribute the hot metal in one or several concussed molds at a constant rate. As I said, the turn disk has a role, initially it has a role that it will supply the liquid steel at a constant flow rate to a multi-strand if required, okay. But today we have other roles also. That is, today with more emphasis on the quality of the steel, and it has far more important function on inclusion control than originally envisaged. So initially what was envisaged to supply the liquid steel at constant flow rate to a multi-strand. Now it is not like that. Now inclusion, there is the turn disk act as an active reactor. It removes the inclusions and it has a lot of provision for the flow design, okay. So flow design such that you can introduce more of type of flow into the reactor and diminish there's a mixed reactor into the reactor, okay, mixed reactor into the turn disk, as well as you want to eliminate the dead zone in the turn disk. That you can do by controlling the operating parameters and the flow diagnostics. You can use the flow diagnostics such that you know what is the proportion of different reactors and then you can improve it. And how you can improve it? Using dams and wears into the reactor. If you use the dams and wear in the reactor, you can definitely improve it. And you can obviously use the flow diagnostic to observe how much improvement has taken place. So what is this? The flow characteristic, as I said, we should promote the plug flow into the turn disk such that the liquid report to the exit stream at a constant superheat, as well as since the plug flow will move through towards the slag, also it will give a lot of chance for the inclusion to be absorbed into the top slag. And also, as I said, we should minimize the CSTR and the dead zone as much as possible. Okay, so these are some of the conclusions. Okay, thank you.